There's a little terminology and notation surrounding linear equations that I wanted to mention briefly. So the first is just a distinction between two general categories of linear differential equations. The first is called homogeneous differential equations. This is a different use, a different sense of the word homogeneous than first order homogeneous equations, where you have some function on your right-hand side of the differential equation that doesn't change if you multiply x and y by a constant. So it's a different sense of the word homogeneous. So a homogeneous linear differential equation is a differential equation just where the right-hand side is 0. And a non-homogeneous differential equation is a differential where the right-hand side isn't 0. We'll see that it's worth concentrating on simple cases first just to get things started. So we'll look at homogeneous differential equations first, and then we'll try to sort of leverage that into figuring things out about non-homogeneous differential equations. Incidentally, if you've taken linear algebra, you might recognize that this is exactly the sense of the word homogeneous as from linear algebra. So if you have taken linear algebra, you're going to have a slight advantage on working with higher order linear differential equations because a little bit of linear algebra does help. And this is just our first indication of that. So that's just a distinction between two broad classes of linear differential equations. You can see that it's kind of annoying to have to write out all of these terms for our order n differential equation. And so there's some nice notation that we can use to abbreviate things a little bit. So the notation is, instead of writing d dx all the time, we're just going to write d. And if we do that, then any linear equation can be written using a polynomial in d. So just as an example, if we have, say, a differential equation, I don't know, d squared y dx squared plus 2 dy dx minus 4y equals e to the x. I don't know, something like this. So this d squared y dx squared, this is just d squared applied to y. Right, this is two derivatives. Each d is a derivative, so this is d squared applied to y, plus 2 times d applied to y, minus 4 times, and then there's no d's in this term because there's no derivatives, equals e to the x. You can see that when we write it this way, y shows up in every term, and so we can actually make things a little shorter by sort of factoring out the y. Now that's not really what we're doing, but it sort of looks like it. So that this gives us d squared plus 2d minus 4 all applied to y equals e to the x. So you can see you could do this for any linear differential equation. If your linear differential equation has coefficient functions of x, so here my coefficient functions were constants, but if you have a linear differential equation that has coefficient functions of x, like this one, I'm going to write a first order equation just so I don't have to do so much writing for this example. So maybe x times dy dx plus x squared times y equals, I don't know, 3. Right, so in this case, you could write this as x times dy plus x squared y equals 3. And then you can factor out the y again. You get x times d plus x squared all applied to y equals 3. So again, we can do the same trick. And so the point of this example is when you have a coefficient function of x, it has to go to the left of d and not to the right. If you put this on the right, if you put this x on the right-hand side of d, remember d is the differential operator d dx. So if you put a function to its right, the derivative hits that function. So we don't want to differentiate this x, so we shouldn't put it to the right. So leave it on the left-hand side like that. So the reason why this is really nice, a really nice notation trick for talking about general linear differential equations is because, right, this sort of operator, this is called a linear differential operator. There are a couple nice things about them. So first, you could just give this a name, right? You might, as a general name for a linear differential operator, you might just call it L, and then your differential equation looks like Ly equals some function of x, right? So rather than writing out the big general form for a linear differential equation, we can just write this abbreviation. Another nice thing about linear differential operators is that they distribute. So if you have a linear differential operator that's built up out of d's and coefficient functions like this, if you have, say, I don't know, d squared minus xd plus 1, actually this is too big. Let's if you have two functions that are added together and you apply this differential operator to both of them, well, this linear differential operator, it does, right? You would hope that it actually distributes like this, and actually it does. So this would give you d squared plus 1 times y1 plus d squared, that's a d squared plus 1 d squared plus 1 times y2. Right. And of course, then you could expand this even further if you needed to for some reason. This would be d squared y1 plus y1 plus d squared y2 plus y2. So this d notation, this linear differential operator notation, the name linear is a good name because linear things should distribute, and sure enough, these differential operators do distribute.